everyone, welcome to my YouTube channel SGKmistry Lectures. In this video, I'll be explaining the entire chapter biomolecules, and also I'll be explaining how to solve various questions on this particular chapter. So let us start with understanding what are biomolecules. So these are the complex organic compounds which are present in the living organisms. Okay, so since they are present in the living systems, the name bio is added, and molecules. Of course, they are complex organic compounds which are present in the living systems. And mainly in biomolecules, we have various classes, that is carbohydrates, proteins, nucleic acids, as well as lipids. So we will be starting with understanding what are carbohydrates, what is their classification, and all the reactions related to this, the important reactions with respect to the carbohydrates. And then we will be learning the other classes of biomolecules. And how do we define these carbohydrates? They are optically active and they are polyhydroxyaldehydes or ketones. So they have either the aldehyde functional group or the keto functional group in them. And along with these, any one of these functional groups, they also have this hydroxy groups. Okay, so that's why we define them as polyhydroxyaldehydes or ketones, or when you subject these compounds to hydrolysis, they yield such units. Okay, and they have the general formula CXH2OY. So they were also, this particular name of carbohydrates was given to this class of compounds because they were initially considered as hydrates. Now we can see here CX H2OY. So this is the general formula. So you can see here there is H2O, right? So first they thought that these carbohydrates, they are nothing but the hydrates of this carbon. Okay, so since they were considered as hydrates of carbon, the name carbohydrates was given based on their general formula. But actually now we know that they are not just hydrates of carbon. They have a complete different structure. They are not the simple hydrates of just the carbon. Okay. And examples of carbohydrates, we know that cane sugar, glucose, starch, all these are the various examples of carbohydrates. Now, there are certain carbohydrates which are sweet in taste. Okay. They are called as sugars. And the most common sugar which is used in our homes is named as sucrose, whereas the sugar present in the milk is called as lactose. So lactose is the sugar present in the milk, and the one that we use at our homes in the kitchen is sucrose. Okay. And fructose is the most sweetest sugar. It is the sweetest. Okay. So the sweet tasting carbohydrates, we generally call them as sugars. Okay. And we also call carbohydrates as saccharides. Now let us look into the classification of carbohydrates. Now, carbohydrates can be broadly classified into monosaccharides, oligosaccharides, and polysaccharides. Monosaccharides, they cannot be hydrolyzed further. Cannot be hydrolyzed further. Okay. So we have examples, simple examples. We have glucose, fructose, we have ribose. So all these are important examples of monosaccharides. Now, when I talk about oligosaccharides, when these oligosaccharides are subjected to hydrolysis, they yield around 2 to 10 monosaccharides. Okay, 2 to 10 monosaccharides on hydrolysis. Okay, we have different examples. Example, sucrose, we have maltose, etc. Okay. Next, polysaccharides, as the name indicates, these polysaccharides, these are the compounds which on hydrolysis yield a large number of monosaccharides on hydrolysis. Okay, large number of monosaccharides. So when they are subjected to hydrolysis, they give large number of monosaccharides as the products. So usually it will be like 100 or 200, 300 like that. So many monosaccharides will be produced on hydrolysis of these polysaccharides. Okay, so we have examples. It can be more than that also. I just gave a number like 100, 200 like that. It can be more than that number also. So large number. This is the general way of defining polysaccharides. So example for polysaccharides, we have starch, we have cellulose. So these are certain important examples which come under polysaccharides. So this is how we classify carbohydrates based on hydrolysis. So monosaccharides, they cannot be hydrolyzed. Oligosaccharides on hydrolysis give 2 to 10 monosaccharides, whereas polysaccharides, they give a large number of monosaccharides on hydrolysis. So this classification is based on hydrolysis. We can also classify carbohydrates based on the reducing properties. Now, what is this reducing properties? So, in case of reducing sugars, they contain free aldehyde group. Okay, free aldehyde or free ketone group. Okay, they have free aldehyde or ketone group. Now in aldehydes and ketones chapter, I have explained that these aldehydes and ketones, they reduce the filling solution and also they reduce the tolerance reagent, right? So these particular reducing sugars, since they have free aldehyde or free ketone group, they can also reduce the Fehling solution or the tolerance reagent. Okay, they give the positive test with this Fehling solution as well as the tolerance reagent. So they are called as reducing sugars. Okay, so under these reducing sugars, we have all the monosaccharides, because in monosaccharides, this aldehyde or the ketone group will be free usually. So because of that, it can the monosaccharides can easily reduce the filling solution or the tolerance reagent. Okay. Especially the monosaccharides which have this free aldehyde or the ketone group. They can act as reducing sugars. Along with monosaccharides, even the disaccharides also, if they have free aldehyde or ketone group, they can behave as reducing sugars. So we will be learning about the structure of monosaccharides as well as disaccharides a bit later. So you will get to know when there is a free aldehyde group, especially when we are writing the structure of disaccharide, how we need to decide whether it has a free aldehyde or a ketone group or not, or how you can decide whether it is a reducing sugar or not. Okay. Next is non-reducing sugar. It's just the opposite of whatever I have explained. So here there is no free aldehyde or ketone group. Aldehyde or ketone group. So because of which they cannot reduce the Fehling solution or the tolerance reagent. Okay. Now, for example, when I'm talking about the disaccharides, if the reducing groups of the monosaccharides, okay, in monosaccharide, we know that monosaccharides join together to give the disaccharide. Di means there are two monosaccharide units joining together to form the disaccharide. So if the reducing groups of the monosaccharide, that is the aldehyde or the ketone, if they are involved in the bonding, then they are not free. So because of which they cannot reduce the tolerance reagent or the Fehling solution. So because of which that particular sugar acts as a non-reducing sugar. Okay, so this is about the general classification of carbohydrates, very, very important. Okay, now coming on to monosaccharides in detail. So monosaccharides, again, you can classify them based on the number of carbon atoms as well as based on the functional group that is present in them. Okay, so if the monosaccharide, if it contains an aldehyde group, then we call it as aldoses. Okay, if the monosaccharide contains a keto group, we call them as ketoses. Now, this is based on the functional group present. So suppose if it contains aldehyde group, then aldose. If it contains a keto group, it is called as the ketose. Okay. Now, based on the number of carbon atoms, again, you can you can classify the monosaccharides into different categories. That is, if there are 3 carbon atoms, then you call it as a triose. If there are 5 carbon atoms, then it is called as a pentose. If there are 6 carbon atoms in the monosaccharide, hexose, or then it can also be higher monosaccharides, but these are the common names, okay? Trioses, pentoses, hexoses. These monosaccharides are the ones which we encounter usually when we are studying about this carbohydrates. Now we are going to study in detail about glucose. Okay, so glucose is an example for a monosaccharide and it has an aldehyde functional group, so it is called as an aldose. And it has 6 carbon atoms, so it is called as the hexose. Now, when you join these, when you club these terms together, we call it as an aldohexose. Okay, because it has 6 carbon atoms and an aldehyde group. Okay, so that is why we name it as aldohexose. Now, glucose can occur freely in nature, as well as it can also occur in the combined form. And it is again present in sweet fruits, it is present in honey, as well as it is also present in ripe grapes, which is again rich in glucose. Okay. Now, talking about the preparation of glucose. So, how do we get glucose? How do we prepare glucose? So, the method of preparation of glucose is from sucrose. Okay. So we have already come across this particular term, sucrose, under the oligosaccharide, or to be specific, it is a disaccharide. Okay. Sucrose is also called as the cane sugar. Okay. So now sucrose on hydrolysis, it will give a molecule of glucose as well as fructose. So from sucrose, you're going to prepare glucose as well as you're also going to get fructose. So this is the method of preparation for both glucose as well as for the preparation of fructose. So if sucrose is, what we have to do is it is boiled with the dilute acid like dilute hydrochloric acid or dilute sulfuric acid in alcoholic solution. So you get glucose and fructose in the equal amounts. Okay, so glucose formula is C6H12O6. So sucrose is C12H22O11. This is sucrose. On hydrolysis, in the presence of acidic condition, we have glucose and fructose as the products. C6H12O6. Fructose also has the same formula. Of course, the structure is different, but the molecular formula remains the same. So this is glucose and this is fructose. Okay. So this is how we prepare glucose from sucrose. Sucrose is a disaccharide. So this is sucrose. Okay, it is a disaccharide which on hydrolysis in the presence of acidic condition gives glucose and fructose in equal amounts. Next, the other method of preparation of glucose is from starch. Okay, starch is an example for a polysaccharide. This also we have come across when I was explaining about the classification of carbohydrates. So, starch. So, this is a commercial method of preparation of glucose. So, commercially, how it is done is glucose is obtained by the hydrolysis of the starch. Okay, so again, we are going to boil the starch with a dilute acid like dilute sulfuric acid at a high temperature of 393 Kelvin, and again pressure is also used. High pressure is also used. Okay, so starch is C6H10O5 N. Okay, this is a polysaccharide. This is starch. So N can be a very large number based on how many glucose units are present in starch. So that's why, and we also know that in the polysaccharides, there are a large number of monosaccharides which are present. So just we are going to represent it as N. Okay. Even from cellulose also it can be prepared. But now let us look into how it is obtained from starch. So you're going to treat it with water. You're going to get glucose. Okay, now since there is N here, I write N and I also write N here. And of course, here you're going to use acid. As I already told, you have to heat it. That is 393 Kelvin temperature and a pressure of 2 to 3 atmosphere. Okay, not a very high pressure, but yes, under pressure, this particular reaction takes place to give glucose as the product. And this is the commercial way of preparation of glucose. So here, glucose is obtained. So this is how we prepare glucose, first from sucrose as well as from the starch. Okay. Now next coming on to the structure of glucose. So how the structure of glucose was deduced? How did they know that which functional group is present in glucose? What is the molecular formula? Okay, based on the various reactions, finally the structural elucidation of glucose was done. So first it was just based on the molecular formula. This was known that Okay, glucose had only the molecular formula was known. So now let me just write the structure of glucose here. So how the structure of glucose was elucidated using the various reaction. So first, glucose was treated with HI and at high temperature. Okay. So they got the product that is N-hexane. Okay. So when glucose was treated with HI at high temperature, it was found that the product that was obtained was N-hexane. So from this, what did they infer? They inferred that 6 carbon atoms are linked in a straight chain. So they knew that all the 6 carbon atoms are linked to one another in a particular straight chain. There was no branching as such because M-hexane was found as the product. There was no branched chain that was no branched alkane that was produced as a product. So it was known that all the 6 carbon atoms are joined one to each other in a straight chain. So next, when they treated glucose with hydroxylamide, okay, they could see that. So here there is an aldehyde group, right? So this was the product that was formed. CH2OH. So we know that whenever an aldehyde is made to react with the hydroxylamide, we get the product as oxide, right? So similarly, here when glucose was made to react with hydroxylamide, they got the product which is nothing but glucose oxide. So when glucose oxide was obtained as a product, they knew that there was a carbonyl group. Okay, because even the keto group also can give oxide. So they knew that there may be an aldehyde or there may be a ketone group, or overall there may be a carbonyl group which is present in the molecule of glucose. So next, they also treated glucose with HCl. So we know that when carbonyl compounds are treated with HCl, they will give cyanohydrate, right? Cyanohydrate. So you have CN and OH attached here instead of the carbonyl group. Then we have CHOH 4 times, CH2OH. So this is glucose cyanohydrate. Cyanohydrate. Okay, so this is about the various products that were formed, and based on this, they could deduce various things. From the first observation, they knew that the carbons are arranged in a straight chain. In the second observation, they knew that there is a carbonyl group. And from the third observation also, the carbonyl group presence was confirmed because the glucose cyanohydrate was formed as the product. Right. So now they wanted to know whether an aldehyde is present or a ketone group is present. So next test was they treated glucose with bromine water. So when you treat it with bromine water, of course, the oxidation takes place. Okay. So it was observed that the CHO group, whatever the functional group was there, it was converted into the acidic group, that is the carboxyl acid group. So it was observed that gluconic acid was formed as the product. Okay, so from glucose, gluconic acid was obtained as the product when bromine water was used for the oxidation of glucose. So the CHO group was converted into the COOH or the carboxyl carbon group. Okay, or the carboxyl group was obtained from the aldehyde group. So from this, what was confirmed that only the aldehyde group can be oxidized to carboxyl group by the usage of bromine water, which is not a very strong oxidizing agent. Okay, whereas the keto group cannot be oxidized to COOH by making use of bromine water. So from this, what they could deduce? They could deduce that the aldehyde group was present in the glucose. So till now, it was only observed that there may be a carbonyl group, and it was confirmed by making it to react with HCl. Now they got to know that aldehyde is the group that is present. Next, they also treated glucose with acetic anhydride. Okay. Now, from this, they could see that there was a pentaacetate product that was formed. Okay, COCH3 acetyl group. Then we have CH2O, CO, CH3. So they obtain the product which is nothing but glucose pentaacetate. Okay, in the presence of acetic anhydride. So let me balance it. So in the presence of acetic anhydride, glucose pentaacetate was obtained as a product. So from this, what was observed, what was confirmed was that there are 5 OH groups that are present in glucose. So they knew that there are 6 carbon atoms. They knew that one of the functional group is CHO, that is the aldehyde group, right? From the observation of gluconic acid that was obtained. And now they also knew that there are 5 OH groups that are present in the molecule. Now, next, they had to confirm what is the nature of these OH groups that are present. Okay, so they treated glucose with HNO3, that is nothing but the oxidation reaction. So they obtained the product that is glucaric acid. Okay, 4 times, and here COOH. Okay, so both the aldehyde group as well as the last carbon atom, that is the last alcoholic, the carbon atom having the alcoholic OH group, so that was oxidized to COOH. Now they knew that this oxidation in the presence of HNO3 mainly brings about oxidation of the aldehyde group as well as the oxidation of the primary alcohol group. So they knew that there is a primary alcoholic group that is present in the glucose, in the molecule of glucose. So this is glucaric acid. Glucaric acid. So from this, they knew the various things. That is, one is 6 carbon atoms arranged in a straight chain. Carbonyl group that is present. In the carbonyl group, they confirmed that it is the aldehyde group. And then they also knew that there are 5 OH groups that are present. Among the 5 OH groups, one of the OH group is a primary alcoholic group. So these were the various inferences that were drawn using the structural elucidation of glucose. But the exact arrangement, that is the spatial arrangement of these OH groups, was given by Fischer. Okay. So now how do we understand the structure of glucose? Okay. So the open chain structure of glucose, it could not explain the various facts. Okay. So this was the structure. One is the aldehyde group. Then we have the primary alcoholic group. Then I'm not going to show the carbon. This indicates the carbon, this atom. Okay. So there will be OH group and H group. Okay. So this was the proposed structure of glucose. Okay. OH and H. So here we have one more OH and H. So totally there are 1, 2, 3, 4, and 5 OH groups and 1 aldehyde group and 6 carbon atoms. 1, 2, 3, 4, 5, 6. Okay. So this was the structure which was proposed, but this is nothing but the open chain structure of glucose. Open chain structure. So you have to just remember when you're writing the structure, the first one is OH. Okay. The first carbon, you're without any doubt, you're going to write the aldehyde group. Next, you're just writing OH in the right side. Then only the next one has OH on the left side. Then again, everything is OH on the right side itself. So this is how you need to remember the structure of glucose. So it was found that when glucose was treated with 2,4-DNP, that is 2,4-dinitrophenylhydrazine, it did not give any positive result. That is, it did not form 2,4-dinitrophenylhydrazone. Also, it shows negative test for the Skiff's test. Okay, Skiff's test, although it has an aldehyde group and it did not form hydrogen sulfide addition product with the NaHSO3. With all of these, the glucose did not give any positive result. Okay, and the pentaacetate of glucose that was obtained by treating the glucose with acetic anhydride, it did not react with hydroxylamide. Okay, the pentaacetate derivative, it did not react with the hydroxylamide, and because of which, again, it was observed, it was Now it was thought about that the CHO group is not free. Okay, so open chain structure could not explain these different test results. 2,4-DNP test was not answered, Skips test was not answered. Again, the hydrogen sulfide addition product was not answered. And then even the glucose pentaacetate, it does not react with the hydroxyl amide. Okay, so with all of these, they thought that, okay, there is no CHO group that is present in the free form. Now, based on this, it was observed, it was proposed that glucose, it exists in two crystalline forms. That is the alpha glucose as well as the beta form. The alpha form, it is obtained by crystallization from the concentrated solution of glucose at 303 Kelvin. Whereas the beta form is obtained by the crystallization from hot and saturated aqueous solution at 371 Kelvin. Okay, so you get two different crystalline forms of glucose. So it was proposed that one of the OH group may be added to the CHO group and it forms a cyclic hemiacetal structure. So it was proposed that the CHO group may not be free to give the results, especially it was found that the 2,4-DNP or the SKIPS test, all of them gave negative results. So it was proposed that the OH, one of the OH group, it reacts with the CHO group of the glucose to form the cyclic structure. And this cyclic structure is called as the hemiacetal structure. Okay, so let us look into how to write this. So first, let me write the open chain structure of glucose. So we know that C here. In the first case, OH is on the right. Next, second case, we have H here, OH here. Again, we have OH here, H here. Again, we have OH and H and CH2OH, right? So this is the open chain or straight chain structure of glucose, and we name glucose as D plus glucose. Okay. So now talking about how the OH and the CHO, because of the combining of these two functional groups, how the cyclic structure will be formed. So here, this lone pair of electrons, it attacks the carbonyl carbon, and this is what happens. Okay, this becomes OH, this double bond O now becomes OH. So two structures are possible. Okay, so now look at this particular structure. In this case, OH is formed here. Here OH will be formed. Now the OH can be present to the right or to the left. There is no particular strict rule that it should be on the right or it should be on the left. The OH that is attached to the first carbon. So if OH is present here to the left, so this is one possibility. The other configuration remains the same. I'm not going to mention the carbon again, all the carbons again. I'm just going to write the OH and H which are attached to the carbon atoms. Okay, OH, H. Here it is CH2, OH. Now this O has been used to form the ring. So it will be a ring structure like this. This O has donated the electrons, right? And this H will combine with this O to form OH. So what I can write is, I'm connecting this carbon with the carbonyl, the previous carbon, which was the carbonyl carbon. And there is oxygen, which is connecting the two groups, right? So this is how I'm going to write the cyclic structure for glucose. Then there is one more possibility. As I already told, OH can be on the right or on the left. Now, suppose if OH is here and H is here, the other configurations remain the same. OH, H, H, OH, OH and H. And again, I'm going to write the same thing. I'm just going to draw the cyclic structure. Since this OH was this oxygen of this particular carbon. See if I number 1, 2, 3, 4, 5. The OH of carbon number 5 was used to form the ring, right? Because it was it was used to attack the carbon in carbon so that oxygen will be here. This hydrogen is used to form this particular C double bond O is converted to COH. So that hydrogen is used over there. So only oxygen is remaining. So that's why I'm going to write the oxygen here. And here, of course, there will be CH2OH. Okay. OH group is at the right. We call it as D plus glucose, and we specifically call it as alpha D plus glucose, or this ring structure is called as the pyranose. So I can also name it as alpha D plus glucopyranose. Glucopyranose. Okay. This is called as the beta structure. So this particular carbon, the first carbon, is called as the anomeric carbon. So carbon number 1, here 2, 3, 4, 5, okay, and 6. So this particular structure is called as the beta D plus glucose or beta D plus glucopyranose. The ring structure is called as the pyranose, and we call this particular structure as beta D glucopyranose. So based on this, based on how the attack of the OH group takes place to the carbon in carbon, we have two different structures, alpha and beta glucose. Okay. And this particular cyclic structure of glucose can also be represented by the Haworth structure. Okay. And here mainly we know that the alpha D glucose as well as the beta D glucose, they differ in the configuration at the C1 carbon atom, which is also called as the anomeric carbon. Okay. C1 carbon is called as anomeric carbon. Okay. And since they only differ with respect to each other, that is the alpha and the beta forms, they only differ with respect to the anomeric carbon, they are called as anomers. Okay. And the C1 carbon also has another name, that is glycosidic carbon. So it can be called as the anomeric carbon or the glycosidic carbon. And the six-membered cyclic structure of glucose is called as the pyranose structure. So that's why we named it as beta D glucopyranose or alpha D glucopyranose. Okay. So let us try to write the cyclic structure, okay, in the Haworth structure. So we know that I just write the alpha cyclic structure, whichever we have written now, 2, 3, 4, 5, 6, so that it will be easy for you to understand how we convert it into the Haworth structure. So this is alpha D glucose structure, which we have just obtained from the straight chain structure, right? So here we have H, here CH2OH, and here it is connected with the oxygen. Now the same thing can be written in the form of the Haworth structure, that is in the ring structure like this. Okay, we now know that in this particular cyclic structure, what is the member? How many members are there? 1, 2, 3, 4, 5, and 6. So that's why I have drawn a 6-membered ring. And one of the member is oxygen, which is already present in the ring. So that's why I have put the oxygen here. Okay. So this is how we convert this particular structure to the Haworth structure. Okay. Now we have whatever these bonds are there with the OH and H, I'm going to represent it this way. Okay. Now, this one will be the first carbon. Now this I'm taking it as the alpha D plus glucopyranose, and I'll also write the structure for beta D plus glucopyranose. Okay. As we already know, the alpha as well as the beta D glucopyranose, they only differ with each other with respect to the configuration around the first carbon atom only. That is the anomeric carbon only. Right. So now, whatever is written on the right here. Okay. So now I'm going to write accordingly. Now, whatever is here on the right will be written downwards in this particular bond. Okay, now OH and H is there. So OH is on the right. So I'm going to write OH here. H here. Okay. Same way here, OH is here, H is here, OH is on the right. So I'm going to write OH here, H above. Okay. Here, H is on the right, OH is on the left. So H I'm going to write below, OH I'm going to write above. Here, OH is on the right, H is here. So I'm going to write OH, H. Okay. Here there is CH to OH and of course there is H also here. CH to OH I'm going to write here and H here. Okay. So this is, it is not exactly like how H and OH are placed here. So this you need to remember. For the last carbon atom, which we are going to write it above here for CH to OH. Now we have written for alpha D glucopyranose. Same way I can also write it for beta D glucopyranose. The only difference is with respect to the first carbon atom. Only the configuration of the first carbon atom. The H which is above here comes below. OH goes above in the case of beta. So I write the same structure, the Haworth structure. I repeat the same things here. Okay. Everything remains the same. Here OH, H, H, OH. Here again OH and H. Again here H and CH2OH. All these things remains the same. Only here in the case of the beta structure, we have H below and OH above. Okay, that is the only difference with respect to the anomeric carbon. This is the anomeric carbon or the glycosidic carbon. Only around the glycosidic carbon or the anomeric carbon, there is change in configuration, just the opposite, right? Then all the other configurations remains the same. So this is how we write the Haworth structure for glucose. So again, we name it as alpha D glucopyranose or beta D glucopyranose. Now coming on to the other reactions of glucose. So glucose, let me write the reactions for glucose. Okay. Now, due to the, first let us see, due to the aldehyde group, what are the various reactions that are shown? So first thing, if you treat it with sodium amalgam, okay. So what is going to happen? You're seeing that, you can see that there is reduction. Okay. So you can see that the aldehyde group gets reduced to the primary alcohol group. So this particular compound is called as sorbitol. This is sorbitol. Okay. So this is nothing but the reduction. So in the presence of sodium amalgam, the aldehyde group is reduced to the primary alcohol group. Now talking about oxidation. Okay. So main two important reactions is Felling's solution. That is the Felling's test as well as the Tollens test. So you're going to use the Tollens reagent. Okay. So here what is going to happen? Felling's solution, aldehyde will give the copper oxide precipitate, the red precipitate, right? So here also the red precipitate is formed. Along with that, glucose is oxidized to gluconic acid. Okay. Same way here, glucose reduces the Tollens reagent and itself gets oxidized to gluconic acid. And here the silver mirror is formed, that is Ag. So this is a precipitate here and this is a precipitate. Here it will be a red precipitate. Here there will be a silver mirror that is formed. So these two tests can be used to find out if glucose is present. That is, suppose if an organic sample is given to you, these two tests can be used to confirm if the glucose has been given as the sample to your, to find out what is present. Right. So if it gives, if you know that it is a sugar, okay, and if it gives the positive test with respect to the Felling's test as well as the Tollens reagent, you know that the given compound is glucose. Okay. There are also other reactions. Now suppose here we have seen due to the CHO groups, it gives different reactions. Again, we know that it also contains OH groups. So because of that, there will be certain reactions. Okay. So first is treating with the acyl chloride, okay, acetyl chloride in the presence of pyridine. So you get glucose pentaacetate. Even you can use the acetic anhydride for this purpose. We have seen it in the structural elucidation, right? So CHO, CO, CH3. CH2, O, CO, CH3. So the OH groups are acylated in the presence of suitable acylating agent. Okay, so this is glucose pentaacetate. Okay, then suppose you treat it with PCl5, so CHO, CHCl4. So we know very well this particular reaction even when we are going to prepare haloalkanes, right, from the alcohols. If you treat the haloalkanes with the PCl5, you're going to see that the OH group is easily replaced by the halogen. So PCl5, if it is used, the OH groups are replaced by the chloro groups, right? So same way here also, since there are OH groups that are present in the uh, glucose. So the OH groups are replaced by the Cl groups. So all the OH groups, there are 5 OH groups. So you get the 5 chloroatom substitution. Okay, so we name it as glucose pentachloride. Glucose pentachloride or pentachloroglucose also can be the name that is given to this particular compound. There is also another way, another reaction. Okay, methanol as well as dry HCl gas. Okay, so you're going to get here OCH3 and H and CHOH thrice. And here you're going to get CH. You're going to get a cyclic structure here. Okay, this carbon and this will form a ring. Okay, so this is nothing but alpha D methyl. Okay, there is a methyl here. Alpha D methyl glucoside. Okay. Along with that, there can also be beta D methyl glucoside. Okay, same thing, only the configuration on the first carbon changes. CH2OH. Again, there is a ring that is formed between these both. Okay. So alpha D methyl glucoside, and this is beta D methyl glucoside. Now coming on to fructose. Okay, fructose is also a monosaccharide, but the difference here is it contains a keto group. Okay, whereas in case of glucose, it was aldehyde functional group. Here it is the ketone functional group. Again, the number of carbon atoms remains the same. There are 6 carbon atoms. So the molecular formula remains the same because we know that aldehydes and ketones, although the functional group is different, they are functional isomers. That means the molecular formula remains the same with respect to the difference in the functional group, that is aldehyde and ketone. Here the number of carbon atoms are same in glucose and fructose. So the molecular formula also remains the same, that is C6H12O6, like that of glucose itself. Okay. And how do we get fructose? This I've already explained when I was explaining the manufacture of glucose. So sucrose on hydrolysis will give equal amount of glucose as well as fructose. So the manufacture of fructose also, you're going to write the same answer. That is hydrolysis of sucrose. Okay. Now, again, it is a natural monosaccharide. It is found in fruits. It is found in honey. It is also found in vegetables. And also it is used as a sweetener. Okay. Now coming on to the structure. So on the basis of its various reactions, it is found that it contains a ketone functional group, and the ketone functional group is present at C2. You have to remember this. Okay. Because it cannot be on the terminal carbon, because if it is on if the terminal carbon acts as a carbonyl group, then it will be an aldehyde. Ketone means on both the sides of the carbonyl carbon, there should be some other groups, right? So it cannot be a terminal carbon. So here, in this case, in fructose, it is in the C2. Okay. And again, it is a straight chain structure where the carbons are attached to each other in the form of a straight chain. There is no branching as such, like that of glucose. And again, it belongs to the D series, like the glucose. And it is a levorotatory compound. Okay, so that's why we name it as D minus fructose. So levorotator is nothing but when this is about optical activity. About this, I've explained in the haloalkanes chapter much in detail. So if the plane of the polarized light is rotated to the right, then we call that particular compound as the dextrorotatory. If the solution of the compound rotates the plane of the polarized light towards the left, then we call that compound as the levorotatory compound. So fructose is a levorotatory type, so that's why we call it as the minus. Okay, so we represent it with minus, whereas if any compound is dextrorotatory, we represent it with plus sign. Okay, so here, since it is levorotatory, that's why this particular minus sign is used for fructose. Okay, now open chain structure, if I have to write, it is similar to glucose. Here there will be CH2OH on one end. Again, on the other end also, there will be CH2OH. Please remember this. First thing you have to remember about fructose, first and the last carbon, both the cases we have CH2OH and CH2OH. Now, second carbon, you already know, it has double bond O, it is a ketone group. Correct? So these things, please keep it in mind before understanding the structure of fructose. Then the next one onwards, this will be here H. Only the first one will be H on the right side. The other two will be OH on the right side. Okay, this is about the structure, open chain structure of fructose, that is D minus fructose. Okay, so I hope it is clear. How do we write the structure of fructose? Okay, in the open chain, especially the open chain structure. Now here also it exists in two cyclic forms, okay, which are again obtained by the addition of the OH groups at the C5 to the carbonyl group. But we know that even if this addition from the C5 occurs to the carbonyl group, the ring structure will have one carbon less, right? Because in case of glucose, this OH group had made a bond with the first carbon atom, since the first carbon was the carbonyl carbon. Here it's not possible because the carbonyl carbon is in C2 position. So that's why the ring will have one carbon less than that of the glucose, right? So in glucose, we call it as pyranose structure. Here, since there are only 5 members in the ring, we call it as furanose structure. I think I can explain it here itself so that it is much easy for you to understand instead of writing it all over again. Okay, so here the OH group from here, see, it comes and attacks this carbonyl carbon. The lone pair of electrons on oxygen, it attacks the carbonyl carbon. And again, this double bond O will be converted to OH, right? And in the ring, there will be oxygen that is there as a part of the ring. Like how we wrote for glucose, the same thing has to be followed here. So let us write the two structures. So again, this OH can be on the right or on the left, okay, based on how the attack has taken place. So if it is on the right, we call it as the alpha form. If the OH is on the left, we call it as the beta. Like how we have written for glucose, the same thing. Okay, so let us write here OH here, okay, CH2OH group itself. Now we have this carbon, this and this have to be written here. So we have C and H here, OH here. Then we have COH, H here. And then we have COH and H here. And then CH2OH. Now this O has been used for making the cyclic structure. So I'll write it in the form of a ring. So this carbon and this carbon are joined together by the oxygen. Okay, now you count the number of members in the ring. 1, 2, 3, 4, 5. There are only 5 members in the ring. So that's why we name it as furanose. Okay. So alpha D minus fructofuranose. Okay, it is again related to that of the heterocyclic structure with oxygen as one of the member in the ring, the 5-membered heterocyclic structure. So that's why the name furanose is given. Okay. So next, this OH can be on the right, CH2OH can be on the left. So I can write it as here OH, CH2OH, here H. Then this things remains the same, CH, OH, here COH, H. All these other things remains the same. All the other configuration around the other carbon atoms remain the same. Okay, so this will be beta D Again, here I have to use minus since it is levorotatory. So fructofuranose, right? So I hope it is clear. How do we get the cyclic structure from the open chain structure? Okay, similarly, I can also write the Haworth structure, okay, using this furanose structure. Okay, so let us write the Haworth structure. So first, let me write one of the cyclic structure so that you the hemiacetal structure, whatever we have got. Then based on that, I can write the Haworth structure, which will be much more clear to you. Let me write the alpha structure, alpha form. So CH2OH. Here we have HOH. The other two carbons have OH on the right side. This is forming the ring. So I'm not going to write the OH. And here there will be CH2OH. So this forms the ring with the oxygen here, right? So this is the alpha D minus fructofuranose, right? So now let me explain how to write the Haworth structure for this particular compound. So here we know that it is a 5-membered ring structure with oxygen that is present in the ring. So I write the 5-membered ring. Two structures I'm going to write, both for alpha and beta, because we know that for alpha and beta, only the difference is with respect to this particular carbon atom. Okay. The configuration with this particular carbon atom, which I have marked. Okay. So now let me write OH here. Now again, let me write the bonds. Here also I'm going to write the bonds, okay, on each carbon. So I hope you know that in the ring, these points represent the carbon atoms, right? These points. These points represent the carbon atoms and the bonds represent like how the OH and H atoms are attached to the carbon atoms. So now in the first case, let me write OH below. Whatever is in the right, I'm going to write it below. So OH on the CH2OH will be on the top. Here H is on the right. So H down, OH above. Here OH is on the right. So I'm writing OH here, H here. Then we have H and CH2OH. Like how we wrote for glucose, the same thing. I'm going to write it here. CH2OH, I'm going to write it above. Okay. Now this is the alpha D minus fructofuranose. Now I can write the beta D minus fructofuranose. Okay. Only the differences with respect to this particular carbon atom. So I write CH2OH below, OH above. Then everything else remains the same. H here, OH here, H here, CH2OH. Okay. So this is with respect to how we are going to write the Haworth structure for fructose. Okay. Now this is about monosaccharides. Now let us try to understand about the disaccharides. So disaccharides, as we know that they are made up of two monosaccharide units. So when you subject these disaccharides to hydrolysis, we are going to get two molecules of the same or different monosaccharides based on what are these disaccharides made up of. So these two monosaccharide units are joined together by an oxide linkage, which is formed by the loss of a water molecule. And this type of linkage between the two monosaccharide units through the oxygen atom is called as the glycosidic linkage. It has a special name which is called as the glycosidic linkage. Now talking about sucrose. So sucrose formula is C12H22O11. We have already seen in the manufacture of glucose that sucrose on hydrolysis gives equal amount of glucose and fructose. So we know that sucrose is made up of two monosaccharides, that is glucose as well as fructose, that is D plus glucose and D minus fructose. So on hydrolysis, it gives D-glucose and D-fructose, right? And it is this sucrose is dextrorotatory in nature. Now, there is one thing you need to remember, okay? Sucrose is, as such, is dextrorotatory. So suppose you take a solution of sucrose and check if it will rotate the plane of polarized light to which direction, you can see that it rotates the plane of polarized light towards the right. So because of which it is dextrorotatory in nature. But once you subject sucrose to hydrolysis, then it gives the dextrorotatory glucose as well as the levorotatory fructose. right? But here you should remember one thing, levorotatory nature, the levorotation angle of fructose is minus 92.4, okay? Minus 92.4 degree, whereas dextrorotation of glucose is plus 52.5 degree, okay? So, although the fructose and glucose are produced in equal amounts, but the degree to which the levo-rotation is done by the fructose is more. Okay, that is minus 92.4 degree. Whereas the degree to which the plane of polarized light is rotated to the right by glucose is lesser. That is plus 52.5 degree. So that's why we called the hydrolysis of sucrose, which brings about the change in the sign of rotation from the plus to the minus rotation, or from dextrorotatory, it becomes now the hydrolysis product becomes levorotatory in nature. So that's why the product is called invert sugar. So we know that C12, H22, O11 on hydrolysis. Okay. This enzyme that was used is invertase. Okay. So since invert sugar is formed, the enzyme is named as invertase because the inversion, that is from plus, that is dextrorotatory, now the mixture becomes levorotatory. So that's why we call it as invertase. This particular enzyme is called as invertase. So you get glucose and fructose. This is glucose and this is fructose. Okay. This is D plus glucose. This is B minus fructose. Okay. Now, talking about the structure of the sucrose, it is disaccharide. We know that it is made up of two monosaccharides, that is the glucose as well as the fructose. Now, it is held together by using the C1 of D-glucose, okay, alpha D-glucose, and C2 of beta D-fructose. Now, first, let us try to write the structure of alpha D-glucose. Now, glucose, we know that it is forming a six-member structure in the Haworth. Now, first let us write the Haworth structure. Based on that, we are going to write the structure of sucrose. Okay. So, we know that in alpha D glucose, the OH will be below, right? So, we have H, OH. And in the other cases, we have here OH, H. Here there is H, OH. Here again OH, H. And here we have H, CH2OH. This is nothing but alpha D glucose or alpha D glucopyranose. Now, let me just write it as alpha D glucose. So now let us try to write the structure for beta D fructose. Now I'm going to invert it and write because the bond is formed between the glucose as well as the fructose. So I'm going to invert. I'm going to write carbon number 2 here, 3, 4, 5 here. Okay. So now in the carbon number 2, we have, in case of beta D fructose, we have CH2OH here. And then, okay, OH. Since I've used the inversion, the structure becomes like this. Okay, now here CH2OH, which was on the top, comes to the bottom. Here H. Now second position, actually H should be below, but now it goes to the top since I've inverted the structure. Okay, so that's why I have to write opposite configuration. So this will be OH here. Okay, now we know that loss of water molecule has to take place. This is nothing but beta D fructose. Now loss of water molecule has to take place and a glycosidic bond should be formed. Now how to write here? You can see there is OH here and there is H here. So it will be removed as water molecule. Let me write the structure here itself and adjust the structure here itself. So now OH from here and H from the other one will be lost. One oxygen is left behind. It is forming a bond this way. Okay. So this is nothing but the glycosidic linkage. Glycosidic linkage. Okay. So I hope now it is clear how the glycosidic linkage is formed between the different monosaccharides. Now you can see that the aldehyde group, whatever was there, it is already forming the glycosidic linkage with that of the fructose, right? So it is not free. The aldehyde group is not free to reduce the Felling's reagent or to give a positive tolerance test. So because of this, the sucrose is also a non-reducing sugar. Okay. Now talking about maltose. Maltose is also called as malt sugar. So it has the formula again C12, H22O11 like that of sucrose. Now here, what are the different monosaccharides that are present? So in this case, we have two alpha D glucose units which are held together by the glycosidic linkage between C1 of one glucose and C4 of the other glucose. Now here the free aldehyde group can be produced in the C1 of the second glucose in the solution, and because of which it acts as a reducing sugar. Now let us try to write the structure of maltose. Okay, so here C1 of one glucose, C4 of another glucose. So we are going to take alpha D glucose units, both the alpha D glucose units. So let me write the structure of alpha D glucose, two such alpha D glucose. Then we are going to join the two carbons C1 and C4. Okay. Okay, so here alpha means OH is below, H above. Then we have here OH, H, here H, OH, here OH and H. Here we have H and CH2OH. The same thing is for this particular glucose also, because both are alpha D glucose. So I'm writing the same structure. Here CH2OH. Here we have OH and H, right? So now, again, when we are looking into this in particular detail, we know that here there is OH and here there is H. So H2O can be removed off. So let me show it here itself. So OH and H. So I'm going to join these two. This is C1, right? This is C1, C2, C3, C4. So these two carbons will, they are forming the bonds. Okay, this H remains the same. H2O is removed off. You're going to get the glycosidic linkage. So this is alpha D plus glucose. This is also alpha D plus glucose. The linkage is between C1 to C4. So this is C1, this is C4. So a glycosidic linkage is formed, right? Now you can see here, this particular carbon, C1 carbon atom, it is free. The anomeric carbon, it is free. It is not involved in any bonding. So because of which this maltose can act as a reducing sugar. It can reduce the filling solution as well as the tolerance reagent. Okay, the anomeric carbon, especially, it should be free. Only if it is free, then we say that that particular disaccharide will be acting as a reducing sugar. Next, talking about lactose, milk sugar. Again, the formula remains the same, C12H22O11. Here, beta D galactose and beta D glucose are the monosaccharides that are present. Okay, and here these are held together by glycosidic linkage. You should also remember this, C1 of galactose and C4 of glucose is used. Now you can see that again, C4 of glucose is used. So because of which C1 of glucose is free. The anomeric carbon of glucose is free. So if the anomeric carbon of glucose is free, we know that it acts as a reducing sugar, right? Let us write the structure for the lactose. So first we need to write the galactose. Galactose is also similar to that of glucose, but it is a C4 epimer of glucose. Now what is called as the epimer? So here, in case of epimers, the configuration around only one of the carbon will be different with respect to each other. So glucose and galactose, the configuration remains the same. Only in C4, there is the opposite configuration. Okay, so that's why we call it as the galactose is the C4 epimer of glucose. So only in the fourth position, in the fourth carbon, the configuration is changed. Now let me write beta D glucose structure. So we have here beta means OH will be above, H below. Here again, the other things remains the same. Here H, here OH, here OH, H, here H, CH to OH. This is beta D glucose. I have to write beta D glucose here because the bond is between C1 of galactose and C4 of glucose, right? So I need to write beta D glucose here. Now I write beta D galactose in starting. First, I need to write the galactose structure, then bond it with the C4 of glucose, right? So galactose, again, beta. So all the, as I already told, it is just the C4 epimer. So because of which the configuration around all other carbon atoms remains the same. So I'm going to write exactly the same in C1, C2, C3. Now in C4, I have to write it opposite. So OH will be here, H will be here. Then again in the other carbons also, it will be the same. Okay. Now OH is here, one OH is here. So OH from here and H has to be removed as water molecule. So the bond will look a bit different here. Okay. The glycosidic linkage. So since OH and H is removed and the bond is formed, the glycosidic linkage looks like this. Okay, so this is how the glycosidic linkage is formed in lactose, which is nothing but the milk sugar. Okay, so this is about disaccharides. Okay, you need to remember what are the monosaccharides that are present in the various disaccharides that we discussed and how the linkage takes place. Now coming on to polysaccharides. So polysaccharides, they are complex carbohydrates which consist of a large number of monosaccharide units. So when they are subjected to hydrolysis, you get a very large number of monosaccharide units. Okay. Under that, we have starch, which is the main storage polysaccharide in case of plants. And it is a polymer of alpha D glucose units. And mainly the starch consists of two components, amylose as well as amylopectin. Now, amylose is water soluble, whereas amylopectin is water insoluble. So let us look into the basic differences between amylose and amylopectin. Amylose is water soluble component of starch. Amylopectin is water insoluble component of starch. Amylose consists of around 15 to 20% of starch, whereas amylopectin, it forms a major part of the starch, that is 80 to 85% of the entire starch sample. If you take, it is made up of the amylopectin. Okay, and amylose, it consists of long unbranched chain. It is nothing, it does not have any branching in its chain, whereas amylopectin consists of branched chain. And here it contains around 200 to 1000 alpha D glucose units, which are joined together in a straight chain. Whereas here amylopectin, linear chains, they are linked by alpha 1,4 glycosidic linkages. Okay. Branching occurs through alpha 1,6 glycosidic linkages. In case of amylase, it is only alpha 1,4 glycosidic linkage that is formed. Okay. Now let us see how amylose and amylopectin is formed. The structure. Okay, so amylose, as I already told, it only involves 1,4 glycosidic linkage and it is only a straight chain structure. And we know that in both of the cases, there's only alpha D plus glucose units. So alpha D plus glucose units, we know that the ring is 6-membered and alpha means OH is downwards, H is upwards. So here we have H, H, OH, OH, H and HCH2OH, right? Next, let me write two more structures to make it more clear because we are talking about polysaccharides here. So here H, OH, OH, H, H, OH, OH, H, and here H, CH2OH. I'm going to repeat the same structure once again because in amylose, it's only the alpha D glucose units which are present. And it's again straight chain structure. There is no branching. And it is clearly mentioned that the linkage is between 1 to 4, right? So H, OH. So this is what how to write the different alpha D glucose units. Now the linkage is between 1 to 4. So first carbon atom, this is the first carbon atom and this is the fourth carbon atom. So glycosidic linkage is between the first and the fourth. So let me write it accordingly. So OH and OH are here. So H2O will be removed. So the bond will be through the oxygen. Same way here also I can write, correct? So this O also I'm going to remove. So I'm going to get oxygen here. So I'll also show for the terminal carbons because it goes on continuing. This goes on because we know that in the polysaccharide, there are so many glucose units or whatever, the monosaccharide units. So it goes on continuing on either side. Now this is nothing but the 1,4 alpha linkage. This is the alpha link. And it is a straight chain structure, whatever is present, that is amylose. Now, in case of amylopectin, in amylopectin, the straight chain structures are connected to each other by 1,4 linkage, okay? And the branching takes place by 1,6 linkage. So, straight chain by 1,4 and branching by 1,6, okay? So, first let us write the two straight chains. I'll write it quickly. Okay. Let me write two straight chain structures. Just I'll write a few glucose units because here also we know it is only the glucose units which are present. That too specifically it is the alpha D glucose units. I'm first going to write the two straight chains. There are many straight chains of course, but I'm just representing a few straight chains. I'll directly write the linkages because already I have explained how the linkages are formed in the amylose structure. So in the straight chain, 1,4 linkage takes place. So I'm going to write the same thing, OH here, H, OH, here H, HCH2OH, here it will be H, here H, here HCH2OH, HOH, okay, here it will be H. This continues. So same way here, glycosidic linkage is formed, HOH. This also I'm going to continue this way. So H, CH2OH, here also H, CH2OH, H, the same thing repeats, H and OH here. So I've just written two straight chain structure which are joined together by 1,4 glycosidic linkages. Now we know that the branching takes place by 1,6 linkage. So let us look into this particular, let me just remove this continuation here. Let me show how it is joined together. Okay. Since they are near to each other, I can show it how it is formed. This is the first carbon. Okay. So it has H here, 2, 3. Okay. And we have fifth carbon. This is sixth carbon. So same way here, 1, 2, 3, 4, 5, and sixth carbon. Now the bonding has to take place between the first carbon and the sixth carbon. So actually there is OH here if it is not involved in the side chain. So this OH here and this OH here will be used for the formation of the glycosidic linkage. So OH and H will be removed as water molecule. So you get a bond here. See here there was H, the OH and this OH here. The bond will be straight. Okay, let me show it clearly. See this O and here there is CH2, that O are joined together. Okay, so this is how 1,6 linkage is formed. That is, the two different chains are joined together by the 1,6 glycosidic linkage between the first carbon and the sixth carbon. So first carbon of one chain and the sixth carbon of another glucose unit that is present in another chain. So this particular linkage is the branching at 1,6 position because the glycosidic linkage is formed between the first carbon atom and the sixth carbon atom of the two different chains, right? So next coming on to cellulose. Cellulose is also an important polysaccharide. So it is widely distributed in plants. Okay, and it forms around 50% of the living matter altogether. So cellulose, again, it is a linear condensation polymer of beta D glucose units. And here the linkage is by beta glycosidic linkage, that is beta 1,4 linkages takes place between C1 of one glucose to C4 of another glucose unit. Present the monosaccharides that are present here are beta glucose units, not the alpha form. So that's why let us write, let me just show 2 units so that it is easier for you to understand. Okay, so beta means H will be downwards, OH will be upwards. Then all other configurations remain the same, H and OH here. Here OH, H, here H, CH2OH. Here we have H, OH. Here we have OH and H. Here we have H and OH. Here we have OH, H, and then the same thing, right? So this is, I'm just showing 2 such units and how the linkage takes place. Then of course it is a polymer, it goes on. And it is a linear polymer. So of course the linkage beta 1,4 glycosidic linkage are used to form the bonds between the different beta D glucose units. Now you can see OH is here, OH is here. So the linkage will be like this. So let me show the linkage, glycosidic linkage. So you're going to get this way. Okay, this type of glycosidic linkage is formed between first carbon and the fourth carbon. First carbon of one beta D glucose with the fourth carbon of another beta D glucose. Then of course this continues. I'll just show it as N because on both the sides the linkages continue by making use of beta 1,4 glycosidic linkage. This is with respect to cellulose. Next coming on to glycogen, which is another polysaccharide. It is a stored carbohydrate that is present in the animals. It is also called as animal starch, okay, because its structure is much similar to that of the amylopectin, and it is present in animals, so that's why it is called as the animal starch. And it has rather more highly branched polymer of alpha D glucose, like that of amylopectin. In amylopectin also there is much branching, but here, in case of glycogen, there is more branching of the alpha D glucose units. It is present in the liver, it is present in muscles as well as brain, and it is also found in yeast and fungi. Okay, the glycogen is present in all of these different organisms and the parts of the body, and it can break by the action of enzymes to form glucose, because we know that glycogen is made up of glucose units. So suppose the body has less glucose in the body, I mean, in the organism, if glucose level is less, the stored glycogen can be broken down, hydrolyzed to give the glucose units. Okay, based on the demand of the body. So how the body requires, if the body requires more glucose, the glycogen which is stored in the liver or muscles, it will be broken down to give the glucose. Okay. Next, coming on to the importance of carbohydrates, it is essential for the life of plants as well as the animals, and they are the major constituents of our food, and they also act as storage molecules, right? Starch is used as a storage carbohydrate in plants, as well as in case of animals, we have glycogen for the storage. The plants, there is cellulose, but certain bacteria, they contain cellulose in the cell wall. And wood is a form of a cellulose which is used in the furniture. So cotton fiber is also made up of cellulose, which is used in the making of clothes. And then nucleic acids, they contain D-ribose, which is a carbohydrate. And also it contains 2-deoxy-D-ribose, which is also the carbohydrates. And most of the naturally occurring these sugars, they have D configuration. Okay, D, they are in the D form. And one more thing is about the treatment of the cotton articles of the natural fibers, which are made up of cellulose. So they are treated with concentrated solution of NaOH. Okay, and this particular process is called as mercerization, which imparts the luster, that is a shiny appearance to the cotton fabrics. Okay, so these are the different things you need to know, some additional information with respect to the applications of carbohydrates, okay, in our daily lives. Next, coming on to proteins. So proteins are nothing but they are condensation polymers whose monomeric units are alpha amino acids. In case of carbohydrates, we know that they are made up of monosaccharides. Here, the proteins are made up of alpha amino acids. And the word protein, it is derived from the Greek word that is proteus, which is nothing but of primary or of prime importance. So based on that, the word proteins has been framed. Okay. Now we also know that proteins are present in the milk. It is also present in cheese, or it can be in pulses or fish, meat, etc. And they are also responsible for the various functions that are occurring in our body. Okay. And chemically, these proteins are nothing but the condensation polymers, and they are made up of amino acid units. Now, what are amino acids? They are made up of carboxylic group as well as the amino group. Okay, so they are made up of both acidic group as well as the basic amino group, and both amino and carboxylic groups are attached to the same carbon atom. Now, for example, if I write the general structure of this amino acids, so NH2 and COOH will be attached to the same carbon atom, and one will be the R group. It can be anything, the side chain that is there. And along with that, there will be also an one H atom. Okay, so this is the general structure of the alpha amino acids. Okay, now talking about the classification of amino acids, very, very important. So when I'm talking about the classification of amino acids, one way you can classify them based on the relative number of the amino as well as the carboxyl groups. Okay, so certain amino acids are called as neutral amino acids because the number of COOH groups and the number of NH2 groups are equal in these amino acids. Examples, glycine, alanine, valine, etc. I'll give the structures of all of these amino acids a bit later. Acidic amino acids, as the name indicates, the number of COOH groups are greater than the number of NH2 groups in the molecule. Example, aspartic acid, glutamic acid. Basic amino acids, as the name indicates, the number of NH2 groups, which are basic in nature, they are greater than the number of COOH groups in the molecule. Example, lysine, arginine, histidine. Okay, so these are, this is a classification of the amino acids based on the number of COOH and the NH2 groups that are present in the molecule of the amino acid. Next, based on their synthesis, we can classify amino acids as essential amino acids. Why they are called as essential amino acids? Because they cannot be synthesized by our body. Okay, they have to be obtained by our body through our diet. So examples of essential amino acids, valine, leucine, lysine, isoleucine, arginine. Whereas non-essential amino acids, they have to be, they can be synthesized by our body. So the term non-essential doesn't mean that these amino acids are not required by our body. It's not that way. They are required. Both essential as well as non-essential amino acids are required by our body. But the only difference is essential amino acids cannot be synthesized by the body. So we have to take these essential amino acids in our food. Whereas non-essential amino acids, they can be synthesized by the body itself. Example, glycine, alanine, glutamic acid, aspartic acid. Okay. Now coming on to the structures of the amino acids, the various amino acids that can be, that you need to know, certain structures you need to know along with the R groups, whatever is present, because questions can be asked regarding which one is basic, which one is more basic, or which one is acidic amino acid. So for all these things, you need to know what is the R group that is present. Okay. So first coming on with the most simplest amino acid, that is glycine, where the R group is H. Okay, so I'm going to write the general formula. So we have R, here we have C, and COOH, NH2 is also attached, and H is also present. So usually NH2 we write here. So I'll just write the H below. Okay, you can write it anyways. I have not written the absolute configuration of this, but just I want to know that R can be the various groups that are possible for this particular substitution. I'm going to write based on that we have different amino acids. Okay, so glycine is the simplest one where the R is just H. So this is the amino acid which is not optically active because here in this particular compound in glycine, The carbon is attached to two hydrogen atoms, right? So two similar groups, so because of which it is asymmetric, it is not asymmetric. So it is not optically active, whereas all the other amino acids can be optically active. Okay, next is the next simpler one, alanine, okay, where the R group is just the methyl group. Next is valine, where the R group is the isopropyl group. Okay, this is valine. Next, leucine. Leucine, we have CH, the similar type like that of valine, but one CH group is extra, CH2 group is extra. So we have CH3. So we are going accordingly so that it is easy for you to remember. Okay. So glycine only H, alanine CH3 group, valine isopropyl. Now leucine also has this similar structure like valine, but one CH2 group is extra. Next, isoleucine. Okay, as the name indicates, isoleucine. Again, it should have 4 carbon atoms in the R group. So here we have CH3 group attached here. Just the iso. So that's why the number of carbon atoms will be the same, but the arrangement is different. So that way you can remember. Next, arginine. Arginine is this you need to memorize, or you can practice. Practicing is much better. Okay, you need to practice the structure of R which is present. So CH2 thrice. Okay, this is arginine. Next you have lysine. We have NH2, CH2 4 times. Okay, so here you can see one NH2 group is extra. So of course this is a basic amino acid. Okay, we have glutamine. That is NH2, CO, CH2, CH3. Okay, it has an acid amide group. Next we have asparagine. Asparagine. So similarly here also there is an amide group, acid amide group with just one CH2 group. In glutamine there is CH2, CH3 group. In asparagine along with the acid amide group there is only one CH2 group. Same way we have glutamic acid. Glutamic acid. Okay, that is same thing like how we have written. Okay, so here there is no acid amide group. Sorry. So since it is glutamic acid, we have an acid group. Okay, carboxylic acid group, but these two remains the same. Okay, so for glutamic acid, CH3, CH2 will be the same. Instead of amide group, we have the COOH group. Okay, so we have COOH. Then the other groups remains the same, CH2, CH3. I mean CH2, CH2 itself, right? Because it is the continuation. Next, aspartic acid. Aspartic acid. Now similarly, like asparagine itself, instead of acid amide group, now there will be acid group. Because aspartic acid, right? COOH, here there is CH2 group. Okay, that is aspartic acid. Next, threonine. Threonine. So it is CH3, CHOH. Okay, this group, that is threonine. Then we have serine. Serine also has an OH group. So OH, CH2 group. Cysteine. Cysteine and serine is almost similar with respect to the number of carbon atoms, but in cysteine, instead of OH, it is SH, a thiol group. Okay. Methionine. Methionine, that is CH3, yes, CH2, CH3. Now, serine has OH group along with the CH2 group. Cysteine has SH group with CH2 group. Now, cysteine is very important even when you're studying about the structures. There is something called as disulfide linkage that is formed between the amino acid residues. So, in such cases, cysteine is the one which is involved in this disulfide linkage because of the presence of the SH. Okay, and here we have cysteine and methionine. So both of them containing the sulfur. So sulfur containing amino acids, if it is asked, you should know that it is cysteine and methionine. Next is phenylalanine. Okay, so alanine, we knew it is CH3 group. The R is the CH3 group. So phenylalanine, we know that the R group will be the phenyl group with the methyl group, that is C6H5CH2. Right. Next, tyrosine. So we have OH, C6H4. Again, this is also, it contains an aromatic ring. Okay, phenylalanine and tyrosine, both of them have phenyl ring. This is in the para position. Okay, so this is with respect to the R group. So you should know that, suppose if question is asked, identify the amino acids containing the phenyl ring or the benzene ring. So you should know that it is phenylalanine as well as tyrosine. Next, there are also amino acids containing heterocyclic ring, that is tryptophan. Tryptophan, we have NH. Heterocyclic rings are the ones in which in the cyclic structure itself you have heteroatom other than carbon. It can be nitrogen, it can be oxygen, it can be sulfur, etc. Okay. So CH2, here the bond continues and here there is a benzene ring. Okay, that is tryptophan. Then we have histidine. Histidine, we have NH. Here. Okay. Again, a heterocyclic ring is present. Then we have proline. Here also there is a heterocyclic ring. Here H, and here we have COOH. Okay. Yes. So this is about proline. Now talking about the essential amino acids, among these, whatever we have written, valine. Okay. Then we have leucine, LEU. Then we have isoleucine. I'll just write it as ILE. Then we have arginine. Then we have lysine. So 10 of them are essential. So next is threonine. Then we have methionine. Then we have phenylalanine, tryptophan, and histidine. So all of these are essential amino acids that has to be included in our diet. Whereas the remaining 10, whatever I have written, so the remaining ones are the non-essential amino acids. Okay. So next, coming on to the properties of amino acids, they are usually colorless and they are crystalline solids and they are water soluble and they also have high melting points and they also behave like salts because they have both basic amino groups as well as the acidic carboxylic groups in them in the same molecule. And since they form salts with acids as well as with bases, their chemical reactions are similar to that of the primary amines as well as they also show similar reactions with respect to the carboxylic acids. There is something to know about Zwitter ion, very important. So in aqueous solution, the carboxylic group, it can lose a proton and the amino group, it is basic in nature. So it can accept that proton and it can give rise to a dipolar ion, which is called as the Zwitter ion. Okay, so it can be something like this. So R CH2, COOH. So there is a carboxyl group. So carboxyl group can easily lose a proton and this proton can be accepted by the nitrogen because the NH2, it is an amino group. So it can be accepted by the NH2 group to form NH3 plus, right? And the COOH group, because of loss of proton, it becomes COO minus. So you can get RCH. This becomes NH3 plus and this becomes COO minus, right? So this particular ion in which you can see both positive and negative charges together, it is called as the Zwitter ion. So it is a dipolar ion because it has both positive as well as the negative charges. Right. Next, coming on to isoelectric point. So, isoelectric point is, we are talking about the pH. So, the pH at which this particular Zwitter ion, it exists as a neutral ion. That is, the positive and the negative charge is equal, and this particular ion does not migrate to either of the electrode. That is, it does not go to the cathode nor to the anode. Okay. So, such particular pH at which this Zwitter ion, it doesn't move, it does not migrate towards of the either of the electrode. That is called as the isoelectric point. Okay. And the amino acids, they have least solubility in water at this particular point as this particular isoelectric point. And because of this, we can easily separate the amino acids based on their isoelectric points. Okay, so they do not migrate towards either of the electrode and they have minimum solubility. So because of which they can be separated easily. Okay, and talking about the optical activity, so except glycine, all the other naturally occurring alpha amino acids, they are optically active because I told you in case of glycine, the R group is H. Already the carbon is attached to one more hydrogen. So since the carbon is attached to two hydrogen atoms, two similar groups, so it cannot be an unsymmetrical carbon, because of which glycine cannot be optically active. All the other amino acids will be optically active. Okay. Next, they can also exist in both D and L forms. So most of the naturally occurring amino acids, they possess the L configuration. So in L amino acids, we usually write the NH2 group on the left-hand side, okay, in the Fischer projection. So we write NH2 in the left-hand side. If it is D, it should be on the right-hand side. So this is the exact Fischer projection. So in the previous 2 or 3 slides, I had written a structure that was just a general structure. It was not an absolute configuration. So L amino acid. Okay, so this is with respect to the amino acids and the properties of amino acids. Now let us talk about the structure of proteins. So proteins, they are polymers of the alpha amino acids, and all the amino acids are linked together by peptide bonds or the peptide linkages, what we call as. Okay. Now peptide linkage is formed between the COOH group and the NH2 group. So there is a H2 as well as there is O here. So it can be removed as water molecule. So basically the amino linkage is CONH bond. Okay, between the different amino acids. So this is how the linkage between the amino acids take place. So suppose I want to write it in the form of a structure. So we have COOH plus NH2. Okay, so here, this way the H2O molecule will be removed off. So we have C double bond ONH. Okay, this is how the peptide bond is formed. This is the peptide bond. Okay, peptide bond. So whatever the products are formed by the linkage of these type of amino acids, they are called as the bond is called as a peptide bond and the products are called as the peptides. Now based on that, we have different types of peptides, dipeptide in which 2 amino acids are present, tripeptide, 3 amino acids, tetrapeptide, 4, oligopeptides means 2 to 10 amino acids forming peptide bonds and making a chain. Polypeptide where more than 10 amino acids join together by peptide linkages and form the chains. Okay. Next, talking about, yes, if polypeptide, it contains more than 100 amino acid residues, then we call it as a protein. Okay. And for proteins, the molecular mass is usually greater than 10,000 atomic mass units or 10,000 unified mass. U is nothing but the unified mass. Talking about classification of proteins, so on the basis of the structure, we have different types of proteins, mainly the fibrous protein as well as the globular proteins. So in fibrous protein, the polypeptide chains are they are parallel to each other and they are held together by hydrogen bonds as well as I already told, disulfide linkages. Okay, so disulfide linkages are mainly because of the amino acids containing sulfur atoms in them. Okay, and here the hydrogen and disulfide bonds are there, and these fibrous proteins are insoluble in water. Example, keratin, which is present in the hair, it is present in the wool as well as silk, and myosin is the protein which is present in our muscles. Next is globular proteins. These are in this particular proteins, the polypeptide chains, they are folded and they are just folded like this into a compact structure. This is what is done in the globular protein. And again, they are stabilized by the intermolecular forces of attraction. There are certain non-covalent interactions that are there, which are stabilizing this particular structure. But these are soluble in water, example, insulin as well as albumins. Okay. Next, on the basis of structure as well as the shape, protein can be studied under 4 different levels. Okay. So we have primary structure. So you can see here in the primary structure, we are just looking into the linear sequence of amino acids which are held together by the peptide linkages to form the chain. Okay. Secondary structure. In secondary structure, we have 2 main types, alpha helix and beta pleated sheets. So this is the alpha helix. And the beta pleated sheet, I'll show the structure. See, this is the alpha helix where there is a helical structure like this. Okay. And beta pleated sheets, we have different polypeptide chains which are held together by these non-covalent interactions like hydrogen bonds. Now, alpha helix is one of the most common ways in which the polypeptide chain, they forms all the possible hydrogen bonds by twisting into a right-handed screw. Okay. With the NH group of each amino acid, hydrogen bonded to C double bond O group. Okay. So there will be NH and CO, the hydrogen bonds that are formed between the NH and CO bonds, and because of which there will be stabilization of this particular structure. Beta pleated sheets, in this particular structure, all the peptide chains, they are stretched out into the maximum extension and then they are arranged side by side. You can see here, they are arranged side by side and again they are stabilized by the hydrogen bonds. Next is tertiary structure. In tertiary structure, it represents the overall folding of the polypeptide chain and again it is responsible for formation of fibrous or the globular structure of the proteins. And the main forces which stabilize this particular secondary or the tertiary structures are the hydrogen bonds, disulfide linkage, van der Waals forces, electrostatic interaction if there are any ions that are present. Next, coming on to the quaternary structure, it is present in proteins containing 2 or more polypeptide chains. So, in such cases, these polypeptide chains are called as subunits. Okay, and this spatial arrangement of the subunits with respect to each other will form the quaternary structure of proteins. Now, how do we denature proteins? So, denaturation of proteins is caused by the physical changes, especially it is because of the change in temperature or even chemical changes like pH. Okay, so when there is change in temperature or pH, then the hydrogen bonds break and even the higher order structures will be disturbed. So the globules will unfold or the helix gets uncoiled. So because of which even the biological activity is also lost. So this particular phenomenon is called as the denaturation of proteins. Okay. So because of which the secondary and the tertiary structures all will be altered. But one thing you need to remember, even if there is denaturation of proteins, the primary structure, that is just the linear arrangement of the amino acids to form a particular chain, that will not be altered. That will be unchanged. Okay, so example of denaturation of proteins will be like coagulation of egg, right, on boiling, and even the curdling of the milk. In this case also, it is denaturation of protein. Formation of cheese is also an example for denaturation of proteins. And some proteins also, they act as antibiotics, which will help in providing defense against the various foreign organisms. And also there will be, if there is any change in sequence of amino acids in a particular protein, it can result in serious diseases. Okay, so like sickle cell anemia, this is one example where due to the change in the sequence of the amino acids, it can cause certain diseases. Next, coming on to enzymes. So enzymes are biological catalysts, so which will help in increasing the rate of biochemical reactions that are occurring inside the body of the living organisms. And most of the enzymes are globular proteins. Okay, so we had 2 different categorization of proteins, fibrous as well as globular. So most of the enzymes come under globular proteins, and they greatly increase the rate of the chemical reactions, especially the biochemical reactions. So like how we use catalysts in chemical reactions, enzymes are the biological catalysts. So even in chemical reactions, we use only little amount of the catalyst. So here also, enzymes are required in very less quantities, okay, to form the products, to convert the substrates into their products. So this is how it is similar to that of the catalyst used in chemical reactions. But one thing you need to remember is the specificity of the enzymes is much more when compared to that of the normal chemical catalysts. Chemical catalysts, as we have seen so many examples, right? Catalytic hydrogenation, all these reactions we have seen in organic chemistry much in detail, right? So in certain catalysts, we can see that it is not very specific. So it may reduce one functional group. Along with that, if the molecule also contains other functional groups, even those functional groups may be reduced in case of catalyst used for reduction. But enzymes are not that way. They are the catalysts which are highly specific. They only catalyze certain reactions, okay, which are specific to them. Okay. Next is characteristics of enzymes: highly efficient, specific in their action, as I already told. For each reaction, there will be a specific enzyme which catalyzes that reaction, and they function under mild biological conditions, not under conditions of high temperature or whatever it is. These enzymes are functional in the normal body temperature in which organism they are present. Okay. So for example, if you want the hydrolysis of maltose, C12H22O11, if I take this as maltose, maltose, we know that it is made up of two glucose units, right? So we have two glucose units, C6H12O6. This is glucose. Now, there is a particular enzyme which catalyzes the hydrolysis of maltose to glucose, and this enzyme is nothing but maltase. So we can see that how specific the enzyme is, right, to bring about the reaction. Okay. Next, coming on to the mechanism of enzyme action. So enzymes are, as I already told, it is required in small quantities, and each of the enzyme will be having specificity towards the substrate on which it acts to give the respective products. Now, the deficiency of phenylalanine hydroxylase enzyme, it brings about the disease called as phenylketonuria. Deficiency of tyrosinase enzyme can cause albinism, right? So albinism is nothing but in which the melanin pigment in the skin is reduced, okay, and it also results in decreased pigmentation of the skin, on the hair, as well as on the eyes. This is mainly because of the deficiency of tyrosinase enzyme in the body. Okay. Along with this, we also have certain common enzymes. So amylase is used to convert starch into glucose. Okay, we know that in glucose, in the starch, there are many n number of glucose units. So amylase is the one which is used in conversion of this particular starch into glucose. Same way, maltase, I already told, maltase catalyzes the reaction of hydrolysis of maltose to glucose. Then we have lactase, which catalyzes the conversion of lactose sugar to glucose and fructose. Then we have pepsin, which is a digestive enzyme which converts proteins to alpha amino acids. Then we have trypsin, which catalyzes the conversion of, again, it acts on proteins, and proteins are converted again to alpha amino acids. Then we have nucleases as the name, and most of the enzymes, just by looking at the names, it is very clear what do they do. So nucleases, they convert DNA or RNA into nucleotides. Then we have urease. So as the name indicates, it acts on urea to break it down into NH3 and carbon dioxide, ammonia and carbon dioxide. Next, we have carbonic anhydrase, which is a very important enzyme, which converts carbonic acid to carbon dioxide and water. Okay, so this is with respect to the enzymes, the various examples of the common enzymes which are very much important in our body for the various life processes to take place. Next, coming on to vitamins. So they are generally regarded as organic compounds which are required in our diet for in small amounts to perform various activities in to perform various biological functions in our body, such as for the normal growth, the optimum growth in our body, as well as to maintain the health of the organism. And based on again, based on whether they are soluble in water or soluble in fat, we have the two different types of vitamins. Water soluble vitamins, they are soluble in water. So since they are soluble in water, they are excreted from our body through the urine. So because of which you need to take these vitamins in our diet. Okay, regularly we need to take these vitamins in our diet. Otherwise, as and when we take it in our diet, since they are soluble in water, they'll be excreted out also. Okay, so excess amounts are excreted in urine. So we need to supplement our body continuously with these water-soluble vitamins. Example, vitamin B1, B2, B6, B12, vitamin C. But vitamin B12 among these water-soluble vitamins can be stored in our body. So that is an exception. So please be clear with the exceptions because such questions can be asked. Which among the following vitamins can be stored in the body? So vitamin B12, although it is a water-soluble vitamin, it can be stored in the body. Okay. Next, fat-soluble vitamins. So they are soluble in fats and oils, and they are stored in the liver as well as adipose tissue. So example, ADEK. So you can just remember this fat soluble vitamins. You can just remember this ADEK. So the other ones, especially the B and C, and the variants in B, that is B1, B2, B6, B12, all these are water-soluble vitamins. So next, talking about how these vitamins are important to us. Vitamin A, okay. So the chemical name of vitamin A is retinoids. Retinoids, okay. And mainly, see, look at the name retinoids. So something related to retina. You can just remember that way. So the deficiency of this particular vitamin can lead to night blindness, okay, night blindness as well as xerophthalmia. So both of these are related with that of the eyes, okay. So again, you can connect it with that of the name, that is retinoids. Next, vitamin B1 is called as thiamine. Okay, so its deficiency will lead to beriberi and loss of appetite. Next, vitamin B2. It is also the name of this particular vitamin is riboflavin. So deficiency can lead to anemia, inflammation of tongue, okay, inflammation of tongue, as well as it can also lead to dermatitis. Next, vitamin B6. It is called as pyridoxine. So it will mainly affect, suppose if the deficiency is there, then it will lead to affecting the central nervous system, and it may also cause weakness, anemia, okay. Next, vitamin B12. Vitamin B12, it is also called as cyanocobalamin. Cyanocobalamin, okay. So its deficiency, very important, it can lead to pernicious anemia. So this can be asked, the deficiency of which vitamin will lead to pernicious anemia, that is vitamin B12. Next, vitamin C, very important. What is the other name? It is called as ascorbic acid. The other name of vitamin C can be asked, ascorbic acid. So its deficiency will lead to scurvy. Next, vitamin D, which is called as calciferol, calciferol. And its deficiency, as you've already studied this in much detail in your lower classes, so it leads to rickets, which is nothing but the bending of bones. Next, vitamin E. It is also called as tocopherol. And the deficiency of vitamin E will lead to loss of fertility in case of males. Lot of loss of fertility in case of males, as well as it can also lead to the degeneration of muscles. Okay. Next, vitamin K. It is called as phylloquinol. And again, the deficiency of this particular vitamin can lead to hemorrhages, as well as it can also lead to the bleeding. So it will increase, the time will increase. So the blood clotting will, the capacity of the body will decrease. So it takes a longer time for the body to clot the blood. Suppose if there is any injury. Okay. So lengthens time for blood clotting. Okay, so this is with respect to the various vitamins, and the conditions of vitamin deficiency in the body is called as avitaminosis. Okay, avitaminosis. And water soluble vitamins, they cannot be stored in the body, and excess intake of fat soluble vitamins, it also causes one more problem, which is hypervitaminosis. Okay, so more vitamin is hypervitaminosis, less vitamin or deficiency is avitaminosis. And vitamin H is also called as biotin. It is neither soluble in fat nor in water. So you need to remember that vitamin H, okay, which is also called as biotin, it is not soluble in water nor in the fats. Okay. So next, coming on to nucleic acids. So these nucleic acids are the polymers of nucleotides which are present in the nucleus of living cells. Now, what are the functions of these nucleic acids? They are mainly helpful in, they mainly play a very important role in the transmission of the hereditary characteristics, as well as their main important function is they aid in protein synthesis. Now coming on to the chemical composition of nucleic acids. Now, when you subject this DNA or RNA into complete hydrolysis, you're going to get these three important products. That is the pentose sugar, phosphoric acid, as well as nitrogen containing heterocyclic compounds, which are also called as bases. Now, in DNA molecule, we have beta D2 deoxyribose as the sugar, whereas in RNA molecule, we have beta D ribose as the sugar. Nitrogenous bases in DNA and nitrogenous bases in RNA, three of them are similar. That is adenine, guanine, and cytosine are same in both DNA and RNA. But the fourth nitrogenous base in DNA, it is thymine, whereas in RNA, it is uracil. There is one difference with respect to the nitrogenous bases in case of DNA as well as RNA. Now talking about the sugars that are present in the DNA. So we know that in case of DNA, it is beta D deoxyribose. So this is a structure of ribose sugar. So we have OH, H. Here we have H, OH. And we have H, and we have H and CH2OH. Let me write it clearly. Okay. So this is beta D ribose. That is whatever the sugar is present in RNA. Okay. Now, when I'm talking about beta D deoxyribose, so here it is given as in case of DNA, the sugar that is present is beta D2 deoxyribose. Now, This is the first carbon atom, second, third, fourth, fifth, right? So now in the second position, there is deoxyribose that is mentioned. So that means one of the oxygen that is present here is removed, and whatever we get the sugar, that is called as the beta D2 deoxyribose. So let me write the structure. So once you know the structure of ribose, you can easily remember the structure of deoxyribose. So all the groups remain the same. Now instead of OH, I need to write here H, H. Then everything else remains the same. So H, CH2OH. So this is nothing but beta D2 deoxyribose, which is present in the DN. Okay, so this is with respect to the sugars that are present in the DNA as well as the RNA. And we also understood about the nitrogenous bases in DNA as well as RNA. The only difference being with respect to the thymine as well as the uracil. So thymine is present in DNA and uracil is present in the RNA. Now let us try to write the structure of the various nitrogenous bases. So you need to have a clear idea about the structure of these bases. So we have the double ring structures, that is adenine and guanine. So we have CH, here C. There is an amino group that is attached here, N, CH. Here we have N, and again double bond CH. This is adenine, which is represented as A. So it has a double ring structure. Again, guanine also, it has two rings which are joined together. So NH here, it's the same thing, only a slight change. Okay, so instead of NH2, we have a C double bond O group here. So since there is C double bond O, so this double bond becomes a single bond here. So NH, this becomes NH. And we have C. There is one NH2 group that is attached here. And then the other things remain the same. So just a slight change with respect to the structure when compared to that of adenine. So guanine, it has a C double bond O group instead of NH2 group here. And here there is a double bond in case of adenine, but here there is a single bond, but instead of N, we have NH. And here in this position, there is an additional NH2 group. So that is guanine or guanine. Next, talking about cytosine, thymine, and uracil, we have alternate CN structure here, up till here. Then we have two carbon atoms. To this carbon, there is NH2 group that is attached. And then here there is a double bond O. So this is cytosine, that is represented with C. Thymine, here also it is a single ring structure, six-membered ring. So again, alternative C and N. So here C double bond O, NH. Here again CH, double bond C. But instead of H, whatever was there in cytosine, we have one additional CH3 group here. And instead of NH2, which was here, here there is a C double bond O group. So that is the only difference with respect to cytosine and thymine. Next, we have uracil. Again, alternative C and N. C double bond O. Here we have NH, like that of thymine. CH. Okay, so this is uracil. Uracil structure is still simpler. So it is like that of thymine. Everything is the same, but there is no methyl group that is additional. Then everything remains the same like that of thymine. Okay, so this is with respect to the various nitrogenous bases that are present in the DNA as well as the RNA. Next, coming on to the nucleosides as well as nucleotides. So before that, let us first understand what are nucleosides and nucleotides, and then let us try to write the structure for the same. Now, nucleosides, when I talk about, they consist of only the pentose sugar and the nitrogenous base. So pentose sugar in the sense it can be ribose in the case of RNA or deoxyribose in the case of DNA. Along with that, there can be the nitrogenous base. That is whatever we have discussed, adenine, guanine, cytosine, thymine, okay, based on the nucleic acid that we are talking about. Nucleotides, they contain phosphoric acid group, a pentose sugar, as well as a nitrogenous base. So here, along with the sugar and base, there is also a phosphate linkage or a phosphate group. So now let us try to write the structure of the nucleoside as well as the nucleotide. In case of the nucleoside, let us first write, there should be the sugar, right? So I write the sugar. So here there is CH2OH. Here there is H. Here OH, H. Let me write the ribose structure. So I've taken it here and here there is H. Now in this position, there will be the base. Okay, whatever the base that we have taken, it can be adenine, guanine, whatever it is. Those bases, any one of the base will be attached to this particular ribose structure in this position. So here we have sugar plus base, sugar plus base. So that's why this is the structure of a nucleoside. Same way, if I have to write the structure of a nucleotide, so we have base, we also have the sugar. Let me write the ribose sugar itself. So OH, H, H, here we have. Now, whatever the CH2OH is there, that is replaced by the CH2 will remain as such. Now, we have a phosphate group. Okay, so this here in this case, we have the sugar plus base as well as the phosphate group. So this is a nucleotide. So this is the structure with respect to the nucleoside as well as the nucleotide. Now next, coming on to how the nucleosides, okay. So nucleosides, once the phosphate group is attached to it, it becomes a nucleotide. Now these nucleotides join together to form dinucleotide, trinucleotide, and so on. Ultimately, it forms the DNA or the RNA based on the sugar that has been taken. So let us see how the linkage takes place. Let me write two such nucleotides. So we have base here. So we have the structures. So this you already know. So here H, OH, OH and H, here H. So instead of here O, we have the phosphate group. O minus, here also O minus. Now we have, let me write one more nucleotide. So here there will be a base, here H, here H, OH. I'm taking ribose itself as the sugar. You can also take deoxyribose. So again, there is a phosphate group since I have written the nucleotide. So these both join together. Now how they link with each other. So now I'm showing how a dinucleotide is formed. So we have the base here, H, OH. Now this is H, right? H, H. This remains as such, CH2O, P double bond O, O minus, O minus. Okay. Now you have to remember that this is the 5' end of the chain and the other end will be the 3' end of the chain. Now how the bonding takes place between the various nucleotides to give, now in this case I'm just showing how a dinucleotide is formed. So this particular, from this part, from this carbon, the bond is formed with the next phosphate group. Now we have again CH2 here. This is of the next nucleotide. So here there is a base H, OH. H, and then it continues. OH, H, and here there is H. Okay, so this is how the bonding takes place with respect to the different nucleotides. So let us see how the numbering is done. Here we know that 1, 2, and 3. So from this carbon, from the third position, here you know that 1, 2, 3, 4, 5. So the bonding takes place in this direction from the third carbon of one nucleotide, that is the third carbon of the sugar of one nucleotide, to the phosphate group that is linked to the fifth carbon of another nucleotide, so that the chain continues on both the ends. So this is how a nucleotide, here I have shown how a dinucleotide is formed. Same way on either side, the chain continues and you can get the different nucleotides which are joined together to form the polynucleotide. Coming on to the structure of nucleic acids, when we are considering it as a whole. So primary structure, here nucleotides are joined by phosphodiester linkages, as I've shown in the previous slide, how the bonding between the different nucleotides takes place to form the polynucleotide, correct? And then the linkage occurs between the 5' and the 3' carbon atoms of the pentose sugars. Now, why this prime is mentioned? Because since we are numbering the carbon atoms in the bases also, so in order to differentiate the numbering in case of the other parts of the nucleotide from that of the sugars, so the sugar carbon atoms are also represented with prime. So that's why we have the 5' end and the 3' end based on which carbon atom of the sugar is free. Next, secondary structure of DNA. So the polynucleotide strands. So suppose we have two such polynucleotide strands which are formed by joining the various nucleotides. They coil around each other and they form the double helix. Now, in the double helix, the backbone, it contains alternative sugar as well as phosphate units. Now, nitrogenous bases, whatever were there. So here, in this case, this is the nitrogenous base. So these nitrogenous bases, they project outward towards the interior of the helix. Okay. So whenever we are considering the double helix structure like this, so this backbone, when I'm considering this is the backbone, so in the backbone, there is sugar and phosphate linkages. Okay. So the two sugar units of the various nucleotides, they are joined together by the phosphodiester linkages. So there are just sugar, phosphate linkages along the entire backbone of this double helix. On the side, there will be these nitrogenous bases which are projected inside. Okay. So now, based on this, again, there is something called as complementary pairing, base pairing. So based on the complementary base pairing, there will be hydrogen bond that is formed between the different nitrogenous bases. And this particular proposal of the structure of the DNA was given by Watson and Crick. So here you can see in this particular diagram. So this is how the helix is formed. And in the backbone of the helix, you can observe that there are sugar and phosphate alternating units that are present in the various nucleotides. And in the inner regions, you can see the base pairing that is occurring. That is complementary base pairing that is occurring because of the nitrogenous bases. So again, there is a particular rule in order for the nitrogenous bases to pair with each other. That is called as complementary base pairing. Adenine always pairs with thymine by making use of two hydrogen bonds, whereas guanine pairs with cytosine by making use of three hydrogen bonds. So you can see here very clearly, see guanine and cytosine, that is GC pairing, you can see there are three hydrogen bonds that are formed. Talking about adenine and thymine, you can see there are only two hydrogen bonds. Adenine and uracil, because in case of RNA, there is no thymine. So adenine pairs up with uracil, again forming two hydrogen bonds. And there is something called as Chargaff's rule, which is very important. So here, what does it state? The amount of purine bases equals to the amount of pyrimidine bases. So purine base of one strand pairs with the pyrimidine base of the complementary strand. So now we know that adenine and if you add together, so if you take adenine and guanine together, that is equal to the amount of cytosine and thymine. So the amount of purine bases is equal to the amount of pyrimidine bases, because you can also see that adenine always bonds with thymine and guanine bonds with cytosine with the help of hydrogen bonding. So total amount of purine bases will be equal to the total amount of pyrimidine bases. So in DNA, AT bonding takes place as well as GC bonding. In RNA, AU as well as GC bonding takes place. Next, coming on to the biological functions of nucleic acids, we know that it is mainly required in case of DNA, the genetic information. It is a reserve of the genetic information, and it is also responsible for transmitting the hereditary information from the parents to the offspring. And it also maintains the identity of the species so that the whatever the changes take place in the DNA, it is only very minimal. Okay, so that it brings about a slight variation, but overall the identity of that particular species is retained or preserved because of the presence of the DNA. We also know that DNA is capable of self-replication or self-duplication when the cell division occurs. So because of that, the identical DNA strands, they are transferred to the daughter cells. So this is what happens during the replication process of DNA. So we also know that the important function of the nucleic acid is protein synthesis. So proteins are synthesized by the RNA molecules in the cell, but the message what is required for the synthesis of a particular protein is taken from the DNA. Okay. Next, coming on to hormones. So hormones are the molecules which act as intercellular messengers, and they are directly secreted into the bloodstream by the endocrine glands. Now, there are different types of hormones, steroid hormones, example, estrogens and androgens. Polypeptide hormones, we have insulin as well as endorphins. Amino acid derivatives, we have epinephrine and norepinephrine. Now, what are the functions of these hormones? They help in maintaining the balance of the various biological activities that are present in the body, and especially this growth hormones as well as sex hormones. They play very good important role in maintaining the growth of the body as well as the development of the body. Next, they also help. Now, suppose you are taking the example of insulin, it helps in lowering and maintaining the blood glucose level in our body. Glucagon, when you talk about, so this acts in the opposite direction. So it helps in increasing the glucose level in the body. That is when there is less amount of glucose that is present in the body of an organism. Okay. And these two hormones together regulate the glucose level. That is insulin as well as glucagon. They both work together to regulate the amount of glucose that has to be present in the blood. Epinephrine and norepinephrine, they mediate the responses to the external stimuli. So this is with respect to the functions of the hormones. Now, before winding up, I want to tell a few more points. So replication, we know that it is a process in which the DNA molecule, it produces two identical copies of its own. Now, when I'm talking about protein synthesis, so it occurs in two steps, that is transcription as well as translation. Now, transcription is nothing but where RNA is synthesized. RNA synthesis takes place. And translation is where the synthesis of the proteins take place. Okay, so now what happens here? First step is transcription where the RNA is synthesized. Next, during translation process, the protein synthesis takes place, which occurs in the cytoplasm of the cell. Now, why this RNA synthesis is required? Because we know that all the three different types of RNA, that is rRNA, mRNA, as well as tRNA, there are three different RNA types. All these three different RNAs are required for protein synthesis. They have a different role to play in one way or the other. Okay, so first the synthesis of these different molecules have to take place, and then the protein synthesis takes place by making use of these different RNA molecules. Next, there is something called as genetic code. This is also something extra. So genetic code, it is a linear sequence of three nucleotides. What we call it as a triplet. And this determines the specific amino acid sequence that has to be present in the newly synthesized protein. This is called as a genetic code. It is like a code which will help the body to understand, especially during the translation process, which amino acid has to be synthesized based on this particular genetic code, that amino acid will be added to the polypeptide chain, that is, which will ultimately become the protein. So all this is controlled by the genetic code which is present in the DNA. Or it can be also present in the RNA, because RNA is also obtained because of the transcription process by taking the code from the or the information from the DNA. Now, it is a biochemical basis of hereditary, and again, it is nearly universal in all the organisms, this particular protein synthesis process, which is controlled by the genetic code, so that which amino acid has to be added to form the protein. So the sequence is decided by this particular genetic code. Okay. I hope this particular video is helpful in understanding in detail about the biomolecules. I have explained how to write the structures of the carbohydrates by keeping in mind the various points while writing the structures of glucose as well as even the disaccharides, all this in detail along with the polysaccharides. Then we also discussed about proteins, vitamins, hormones, as well as nucleic acids. The nucleic acid structures along with the purines as well as pyrimidine nitrogenous bases, how the nucleotides are formed, all these things have to be kept in mind with the structures. So I hope it is helpful, and thank you so much for watching the video. So I'll be explaining and discussing about the previous year questions from this particular chapter. I'll be coming up about with this in the next video. So thank you so much, and subscribe my channel for more such informative videos. Thank you.